that would be the one that's at peak. But the other two may be somewhere below peak, and they may also be, they may have enough voltage potential to have a different diode pair open and running. And we don't know that. But if we look at it on this side, all we're gonna see is whatever one is the highest, okay? If I look at it here, then I'd see the whole behavior of that one unit, okay? Or more aptly, if I looked at it right here, I would see it. Okay, and then same idea, but with the Y wound. So now here's a question for you. You guys are gonna get really mad at me when I ask this.
There we go.
You're gonna get mad at me because there's not much I can do, but I gotta ask it. Okay, I'm gonna go there. Gotta do it.
Somebody's an FAA test question?
Oh, it's way worse than that. Oh, way, way worse than that. So these wires are gonna come out here. I'm not gonna draw on the screen. They're gonna come out here like this. And we're gonna attach them to the bus. Okay, we're gonna have all the loads coming off the bus. And then out here, we're gonna attach to our battery. Like that. Okay? And all the loads come out here like this. Okay? Based on what you see there, which is negative? Red or blue?
Blue.
Red.
Blue.
How many say red? Raise your hand. Okay, how many say blue? Oh, the company. How many are wimps? Yeah. Okay. What does the battery do when it puts out electrons? Does it put them out the positive end or the negative end?
Negative end.
Okay, so we've said electrons are coming out to the bus,
Right.
to right here, right? Okay, and I actually need to separate that. Okay, that means if electrons are coming out to the bus, the electrons need to be coming out to the bus from the battery as well, right? So this has to be negative into the battery, and this has to be the negative end, right? So we're going to pull electrons in here, and we're going to pull electrons in there, and push them out there.
So is the red.
So blue is the negative side, red is the positive side in this particular drawing. For the case of the battery, when we start charging the battery, we're going to shove electrons back down into it and then pull them back out here and shove them back down into it. Okay? But while the battery is discharging, it's going to go negative, just like the generator goes negative. Only when we have to recharge, so we start, wah, 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 bum, this is now depleted. Well, it just becomes another load. Okay, electrons come out through the light bulb, back to positive. Electrons come into the battery, back to positive as well. Okay? Gotta be that way because that's the way the diodes are drawn. I'm getting stink eye over here. How about stink eye anywhere else?
No answer.
So,
Blue.
tell me this.
Negative. The other's positive.
As far as I can tell, I got negative here, positive here. It's all bolted and hooked up and right through there. And boom. When I turn this thing off, isn't the battery going to discharge?
Sure. Sure. Yeah. Why not?
Hmm? It's all hooked up. Somehow I got to disconnect things, or the battery's going to discharge, right?
Yep.
Switch.
Huh?
Switch.
They're all one-way check valves, aren't they? Battery can't go back the other way. It's like cows got no down genes. They only go uphill. They can't go downhill. Same thing true here. I can make the electrons go this way, they can't go back the other way. The battery cannot discharge through this, unless one shorts, which is extremely rare. Out of overhauling hundreds of these units, I think only once. And in fact, I think the one time that I had one shorted, somebody jump-started the vehicle, tried to jump-start it, hooked up backwards. That blows up a lot of things. Diodes don't like being hooked up that way. Yeah, this thing automatically prevents reverse current problems. The commutator style generator, we said it's an electric motor. If you don't disconnect it, it will try to keep the engine, it'll keep sucking the battery down when you go to shut it off. Here, it's automatic. Yet one more thing, one more advantage this particular device has. So here's the rub from the manufacturer's end of the game. It's like, it's easier to make, it costs less, it works better, I have less customer complaints, and it's brand new, so I'm going to charge you more for it. That's pretty cool, huh? You got to have one of these on your car. You'd be the only one on your block with one of these newfangled alternators. Got to have one, right? We're going to charge you more for it. More for something that cost us less. It's like when they first started introducing unleaded fuel. Most of you probably want a live fuel. They said they took the lead back out and charged more. There's no way they put the lead in and then took it back out. They never put it in. They charge you more anyways. Okay, so for the purpose of FAA test questions or any other fool who will ask you, the rectified generator, rectified DC generator or alternator is self-limiting. But I assure you, having seen many, many smoked alternators, you could overheat them long before you hit self-limiting speed. One of the things I really do like about working in the aviation industry is they give you real numbers. The law requires if you're going to sell this thing, you got to tell me how many amps and what voltage it'll operate maximum continuous duty, and that means for the life of the unit. If that's 100 amp, I can leave it at 100 amp for the entire expected lifespan of the unit, and it won't disintegrate on me. It doesn't exist in the world of experimentals. There's a number of flaws in the world of experimentals where they're putting automotive units into experimental airplanes, automotive alternators in ways that are magical. And I've had multiple conversations with several of the companies the kit manufacturers. I've got one of them, one of the better ones, Vans, convinced that what they're doing is dangerous. So they finally just said, we're not selling these anymore, and go to an aviation version. Because little units weren't made for it. An automobile engine, inline engine, nice, big, smooth, round counterweight. Oftentimes they even have counterbalance things going on, but they're so much more smoother than an old dinosaur Lycoming engine or Continental with a big noodle out there flopping around, producing way more power per power pulse than an automotive engine ever comes close to. They just tear up this little stuff. Not to mention that, guess what spins differently? Airplane engines don't spin the same direction automotive engines spin. The only automobile engine that spins the same direction as airplane engines is Honda. All the rest spin the other way around. So if you put a fan on there, it's going the wrong direction. It's not cooling. Yeah, nobody ever thinks about that kind of stuff. Okay, so output can be a function of rotor RPM, and it can be a function of field strength. Really, magnetic field strength, which translates into magnetic field current. Okay? That's a true statement. The problem is we don't get to control RPM. We don't get to say, well, here's the RPM I'd like because I've got the headlights on, I've got the high beams off, I've got the rotating beacon on, I've got the taxi light on, and the heated pitot tube is on. And so I'm going to set the RPM to be just nice for that. Okay, I'm setting the RPM for taking off, or for cruise, or for landing, whatever that needs to be. So my only other option is to vary the field current. Now, the other thing that's sort of kind of important, let's have a little bit of a discussion about this, is I could try to keep the current appropriately matched to whatever my current demands are. And voltage, whatever. Whatever. The problem is the preponderance of users are designed to operate at a very specific and fairly narrow voltage range. So it's for very different reasons, but I'll pick the light bulb by example. The filament in a light bulb is designed to operate at a very specific temperature. That temperature is set by the voltage. The reason they want that temperature is because that determines what resistance. It's a negative, or it's a positive coefficient temperature, or a positive coefficient of temperature to resistance. They want it at a very specific temperature so that it maintains a very specific resistance, so that it operates at an exact amount of power or an exact amount of wattage. If it operates at that wattage and at that temperature, the metal will be smoking hot. I mean, it's putting out light, right? And what's going to be happening is the metal is actually going to be gassing off and circulating around in the bulb and reforming back onto the filament, and gassing off and circulating and reforming, and gassing off and circulating and reforming. After a while, you may eventually start to see a little bit of mirroring on the inside of the bulb, as some of that metal, it's usually tungsten, doesn't really redeposit. It deposits out on the inside, ionically deposits to the inside of the glass. It's kind of the same thing when they put mirror coating on your sunglasses. Okay. The light bulb manufacturer has designed that bulb to last as long as it can, or as long as they want it to, based upon a fairly narrow definition of voltage, plus or minus about a volt. So they want to see that thing operate at 12.68 battery voltage to 13.68 generator voltage, and not too far either way, or whatever it happens to be. That's true of electric motors, that's true of starters, that's true of all kinds of different loads. Voltage control is sort of the name of the game. And you can see that as evidenced by those of you guys that have magnetos on your motorcycles. What happens down at idle? What happens to the headlight? Flash, 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 flash. Gets kind of dim and flickers a lot. It gets bright again. It gets bright again. Okay, that's not very functional. Okay, Grandpa in his Jaguar does not want the headlights going dim and bright and dim and bright. He's already got enough problems with strokes and other things going on. Doesn't need to think he's having another one, right? Okay. So, voltage control is the control of choice for all generators. In the world of AC, because of inductive and capacitive reactance, we don't get a choice over RPM because we're going to keep it at a very fixed RPM due to maintaining frequency. It will either be at 400 cycles per second or 60 cycles per second. And when I say cycles, that doesn't necessarily mean RPM of the armature. We've now discovered that I can get a full cycle at a 36th of a revolution. But whatever generates 60 AC cycles on each phase per second, that's what RPM it'll go at. If I have a turbine engine driving it that needs to be at 40,000 RPM, guess what? There's going to be a gearbox in there somewhere, right? Some kind of a transmission lowering the values down. Now, from the perspective of using any combustion engine to run this generator, if it's a ground-based unit and you're aiming at 60 cycles per second, you're gonna design your engine to operate at that specific RPM, and all of its pumping action, everything, timing, everything's all gonna be aimed right at that RPM, so you get the greatest bang for the buck out of the engine. Okay, so that's kind of what I'm saying there. And in AC, typically we'll see 60.01001. Occasionally it gets down to 59.9999, somewhere in there. We got the little panel over here that I look at and watch it, but I also have a pretty high resolution frequency counter that takes it out to about 8 decimal places. And they keep it pretty tight. And when we start talking about inductive and capacitive reactance, you'll see why. Okay, so in the world of AC, we keep the RPM very constant, so what happens when the sun goes down, everybody turns the light on?
More draw.
Load goes up, right? They gotta turn the nuclear reactor up. Well, they can't bring the RPM up, so the only thing they can do is make the field magnet stronger. Okay? Now, in truth, if it's enough, they'll bring another generator online, and a third one, and a fourth one, and, okay? And in fact, global, in the United States, actually in North America, we moved the whole value of the power grid is there are phases of power. So in other words, there's a morning period where there's a lot of power used on the East Coast, so a lot of power gets sent that way, and then the power gets sent to following that window of time across, then it starts dropping down, then as the afternoon starts hitting, air conditioners start coming on, there's the second wave of sending the power back that way, and that's kind of why we, the person you pay the power bill to doesn't produce power, they're a vendor. Sempra Energy, they don't own any power plants anymore.
It's the genie.
They're vendors now. They buy and sell
Buy
power.
it from SoCal Edison. Probably several people that buy from it.
So for all of these systems, really field current control becomes the name of the game, and we do it based upon output voltage. So we got this little guy in there with the voltmeter, and he's going, okay, and he's watching the voltage, he's watching the voltage, and he's got a big rheostat, and he turns the field current up and the field current down, and field current up, field current down, and he's sitting in there doing that, okay? Well, it's actually not quite that way, but essentially that has to happen. If it wasn't automated, think about what the poor flight engineer is doing inside the 4-engine airplane while the pilot's going through combat gyroscopic whatever, okay? RPM's going up, power's going up, the pilot's doing all this stuff. Poor flight engineers, man, he's dialing those, just doing all kinds of stuff to keep the generators up and on board with each other. Well, there's no possible way a human could do it. It just absolutely would not be possible. Has to be done through some kind of automated means. So essentially what we do, this is in a magnetic field, right? We've said it takes time to build up. We've said it takes time to collapse. So if I just take a switch and go on, off, on, off, on, off, on, off, my magnetic field's going to be going boom, boom. And if I spend more time on, off, on, I'm going to start doing it up here. If I go the other way and go on, off, my magnetic field is going to start collapsing through each cycle. So it's kind of like, not a lot of magnetic field. On the other way, if I go the other end of it, leave it on for a while and just off for a little bit. So by switching on and off, we can get a magnetic field to stay alive, but sort of going up and down. When we're off, we're not expending any current. When we're on, we're expending current, but when we're off, we're not expending any current. Now, I could also do it with a big resistor. But when I start increasing the resistance, isn't the resistor going to get hotter? So I could do it with a big resistor, but it's going to use a greater amount of energy. So the switching technology for smaller units is a good way to go. For bigger units, you've got enough current that your switch isn't going to last very long, because we're turning it on and off really fast. I did it slow, but it's more like it's switching pretty quickly. Okay, so if I have to run a field at 3, 4, 5, 8, 10 amps, that switch isn't going to last very long. It's not going to last 2,000 hours or whatever the duration of operation. So now I'm going to have to go consume a little bit more energy and go to an analog device. The downside of the switching technology is when I open the switch, what happens to the magnetic field? It starts trying to collapse. What does that do to the circuit? Creates a little pulse on the circuit. So it starts making a little bit of noise on the circuit. So the switching type regulator, which is true of most common regulators, does make a little bit of noise. So noise, noise, you're not very noise tolerant because you've got comm radios or something else, or nav equipment, you're going to have to address that. Okay? All right, so it's a good place to stop. Get one last measurement